Okay, welcome to your ETS Math 022 practice question number 41. This question is brought to you by the number 5, the letter P, and one little Microsoft Surface that is not my friend today, or maybe any day after this. So, we are looking at this model. It is a pentagon with a star inside, or a pentagram as some would say, and it wants to know there are 3 ways that this model would be useful, and then one situation in which this model is not useful. You're searching for that one situation in which this model doesn't make any sense. So I see first of all just one that makes a lot of sense right now. This model does in fact show the number of diagonals in a regular pentagon. So I'm going to put a smiley face on this. This is not my answer choice that I would put like on a Scantron. But yeah, I mean, I can see the number of diagonals, and that's a pentagon, so good for that. If you had 5 teams and everyone played everyone else, like here's each of those teams and every one of those teams played everyone else, yeah, that would show it, correct? Because you would see if this is team A and this is team B, C, D, and E, you could see that A plays C, C plays E, B plays E, A plays B, B plays D, A plays D, A plays E, E plays D, D plays C, and C plays B. So yeah, there are 10 games, and that's a really good way to see how many games total you would be looking at. So I'm going to give that one a smiley face too. That's not going to be my answer because I'm looking for the bad situation. It also says here, I'm going to skip B because I know that's the answer, and talk to you why C is a good model here. If you think about it, 2 element subsets of a set of 5 elements, that's exactly the same thing really as everyone playing everyone else in a bracket of 5 teams. So C also is a good way to show that. I want to show you why B is the answer for the bad thing that this models. And it's saying basically, if you've got 5 people who can sit at a table having 5 sides, and it says that it's a pentagonal table. So basically what that is setting up here is that you've got this table where for whatever reason it matters what side these people are sitting on. So it's going to look kind of like this, a pentagonal table. Then you've got a person A, a person B, a person C, and so on. There are actually 120 different ways that 5 people can sit at a pentagonal table where the sides are different. And I don't know, one of them has the view of the TV or something. One of them has a view of outside. So if there are 5 different ways that you could sit there, 120 different ways that 5 people could sit at a 5-person table. And that actually is a permutation. If you've got 5 seats, and I think of it kind of like this, just imagine, actually, let me show you. Imagine that the seats are sort of like where a side of the table, whoops, green and blue and yellow. All right. So if you imagine that, first of all, if you're just sort of looking at how many possible ways, let's say that you're seating people in the first seat first. You actually have, if the 5 people are standing there, you have 5 different ways, 5 different people that could be selected for that purple side. Okay. And then let's go to the pink side. Since you've already selected a person for the purple side, there are only 4 people left that you could select for the pink side. And then for the green, if you're randomly selecting, there are now 3 people left. For blue, 2. And for yellow, 1. So if you multiply those, 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is still 120. There are 120 ways. This particular picture in no way demonstrates that. It demonstrates something about 10. So that's why this one is B, because that is not a good model that would help you to understand a permutation.